Hello and welcome to the 101 on tensors. Let's start with some very basic introduction. We have our PyTorch tensors, which are basically forming the structure to work with the variables. And you can imagine to be the tensors pretty similar to NumPy arrays, but they are much more powerful, as you will see. Because that is one of the reasons they can automatically calculate the gradients. And I will show that in a second how this is working. And then they're also storing the information about dependencies to other tensors. So these two last items here are the main features which are making the tensors so extremely powerful. But let's take a look at some example. So let's speak about automatic gradients. That is meaning, like the name is saying, the gradients can be calculated automatically. And you can see here I have created a tensor x with a value and also with the property requires grad equals true. And then we have another tensor called y, which is a function of x basically. And then just by calling the backward function on y, you are getting all the gradients updated. And then if you're printing the gradient of x, you can see like magic that you get back the value of 31. And if you plot that, like you can see it here at the right hand side, you can see here this is actually a representation of this function. So we have y over x. And then if we calculate the derivative of y to x, then this will provide for a given position of 1 the derivative of 31, which is basically the slope at this position of the curve. Great. But what can you do with that? So we will come to that. Let's imagine that you're working with a very simple network. So you have an input x and you use it to calculate another variable y, which is then itself being used to calculate z. So here you can see it. We have x, y and z, and we have the interlink between these. So y is based on x and z is based on y. So then we have certain formulas defining how these links are defined. And this is basically what we can call a forward pass. Later on, when we're working with our networks, we are using the very same terminology. So we are always saying we are making now a forward pass through the network or a backward pass. Now here we'll see what this basically means on the most simple examples. Because then the backward pass, that is basically the backpropagation, which means that in this step the derivatives are calculated. So the derivative of z to y and the derivative of y to x. So basically you can calculate the change of z based on a change of x. So here you can see the derivative of z to x, and for this you can apply the chain rule. And if you're doing that based on these formulas which are given here, then you can calculate this first derivative to be 5 and the second one to be 3x squared. Alright, so far this is not a very super network. We only have an input node, an output node and a hidden node, and we don't even have the weights. So let's now take a look at how the weights could be added and how the weights can be updated. So here we have the same network, x, y and z, and then we have the weights assigned. So we have a weight assigned to z and a weight assigned to y. So we want to calculate our output z in the end, and we can expect that this is just a calculation because the true output deviates from our calculation. So we are only getting closer and closer to the reality. And for this we are calculating some error, which is basically the difference of z and t, and to have only positive errors, usually this error is squared. And then you can see here I have attached the weights. And actually the weights can also be considered to be nodes, very similar to the other ones. And then if you treat them as nodes, then you can consider z to be a function of y and w2. And then you can go backwards in the chain. And basically what the optimizer in our network is doing, it's updating the weights based on these gradients that we are seeing here. And then to get closer and closer to a real network, all we have to do is scaling. So let's assume now that we have multiple inputs. So now we have two inputs, x11 and x21, and then a hidden layer and then an output layer. Then we can also assume that we have a fully connected network. So our x11 is connected to the first node of the hidden layer and the second node of the hidden layer. The same holds for x21. And then you can see the dependencies. So x12 is depending on the first input node and the second input node, and the same holds for x22. And then the output layer is taking a look at one layer before, and it's depending on x12 and x22. So this is basically forming our forward pass. And then for updating the weights, all we have to do is calculate the derivatives, and then we can get the weights basically. So let's take a look at some example. Let's say we are having these formulas which are defining the relationship between x12 and the input nodes and x22. And also y is depending with this formula on the hidden layer. Then all we have to do is calculating the gradients. So you can pause the video and recollect your math knowledge and check all the calculations that I have done here. And I come up with these two different derivatives. And then with a given x11, we can calculate the slope to be 44 for dy to dx11 and correspondingly the other derivative. Alright, that was the introduction on our tensors, and now in the coding lecture you will be able to see all this in action. We are going to create these graphs on our own and perform these calculations directly with PyTorch. Thank you and see you there.